Great. Well, good afternoon, everyone. I'm John, and I'm the Accuracy Team Lead at Speechmatics. So Speechmatics provides the most accurate and inclusive automatic speech recognition on the market right now, and we provide that to other businesses to plug into their services. So an example of this is we sell a lot to the call center space. So we have customers like Veritone who use us for that. And then we do lots of media broadcast in real time as well. So today I'm going to be talking about word error rate and why actually I think it's becoming obsolete for evaluating speech recognition. Now, word error rate is actually quite often misaligned with what we care about as developers or consumers of ASR. And that's actually a really big problem because a lot of the time, multi-million-dollar deals can hinge directly on small changes in this metric. And if it's a big decision, you really want that metric to align well with human judgment. So Speechmatics has been working on a novel alternative to word error rate, one that truly understands the meaning in our transcripts by harnessing the power of large language models. So we're going to be talking a bit about that as well, which hopefully will be exciting. First of all, let's talk about what word error rate actually is and how you calculate it. So word error rate is the primary accuracy metric in speech recognition. It's been used since the dawn of the technology, and it's very easy to calculate. So what you do is you have your gold standard reference transcript that someone has written up. Someone's typed this up based on what the person has said. And you get an alignment with the output of your speech recognition system. And from there, you can count up the errors. So you have substitution, insertion, and deletion errors. And you can see the formula here. It's just a proportion of the total number of errors over the number in the reference transcript. And you're driving word error rate to 0. So that means you have no errors. But what are the problems? So first of all, to actually get a really accurate alignment, you have to put everything in lowercase. You have to remove punctuation before you do that. And that's, those things are actually really important for readability of our transcripts. And the fact that we're removing those is not ideal when we're evaluating. Also, there's an intrinsic flaw in this. And what I mean by this is if we're driving word error rate to 0%, that's actually very difficult if there's errors in the human transcription. And as you're all aware, there's lots of ways of writing the same thing that has been said. So for example, dates is a good example. You can write that in lots of different ways. And if your specification doesn't match what's in the reference transcript, word error rate is going to really penalize you heavily. Also, each error in word error rate is evenly kind of each error has an even distribution, which isn't ideal if you have errors which might cause misinformation, for example. You want to penalize those more. So this is all to say word error rate just isn't very smart at all. So let's look at some examples here. So in the top right, you can see the reference is I'm a 5-year-old kid, and the ASR is I am a 5-year-old kid. So you can see there's not big problems here other than the difference in specification of this written form output, and I'm versus I am. But this leads to 5 errors. There's 2 substitutions and 3 insertions here. So when you calculate word error rate, it's over 100%. It's 125%. In the bottom example, we just have one error, one substitution error of have and haven't. But that causes misinformation about the fact that you haven't sent a message, or you have. The word error rate here is only 20%. So you can see, that's a much worse problem, but the error rate is telling us that it's good compared to the other one. So what's an alternative? So there's something called the NER model, and not to be confused with named entity recognition here. But essentially, this brings in a weighted evaluation of these errors. So we have 3 different types here, minor, standard, and serious, and they each have the penalties kind of shown on screen there. And what's going to happen here is as a human kind of goes through the errors in the transcripts, they're going to start to add up how many of the minor errors they have and total up what score they have for each of them. And then you have this formula on the right here where it's just the sum of the penalties over the number of words. It's quite similar to word error rate, but the penalties are not even. So this is much better at capturing loss of meaning in the ASR output, but the big problem here is we need a human in the loop, and this is really expensive to do. So we're going to look at some examples now. So first of all, a minor problem. I don't believe executives should be able to overturn a decision. So there's just one substitution there, and for in. You can read through it. It's not a big problem. Standard, this is my sister who works at the hospital, when the correct one doesn't actually have the question mark there. So there's a small kind of change in meaning there. You would read it differently. Then a serious one, you omit the word suspected before murderer. This is a huge problem. Imagine having that in a transcript after a court case. This is a big problem there. So that one would be a serious error. We're going to come back to NER, but we're going to take a bit of a sidestep and talk about large language models. So large language models, they're essentially trained on text data, and all they do is they take in a context of words and they try and predict the next one. So you see this all the time on your phone if you're texting, and you kind of have 3 options and you choose one of them instead of having to write it out yourself. Everyone is scaling language models at the moment. So back in early 2019, we had GPT-2 from OpenAI, and then more recently, we've had GPT-3. So we've gone there from 1.5 billion parameters to 175 billion parameters. And then in April this year, we had Palm, which was Google's language model. That had 540 billion parameters. That's off the chart. So they're scaling compute data and parameters to do this. And the reason they're doing this is you get incredible few-shot learning performances on hundreds of tasks. You don't have to fine-tune these models on each task. You just have to give them a couple of examples of, say, reading comprehension in the prompt, give it the one you care about, and then it will be able to solve the problem. So let's just look at an example of large language models doing question answering. So this is an example that completely kind of blew me away. So the input here, Michael is at that really famous museum in France looking at its most famous painting. However, the artist who made this painting just makes Michael think of his favorite cartoon character from his childhood. What was the country of origin of that thing the cartoon character usually holds in his hand? That's the input. Now, one word at a time, the language model is going to predict the following. The most famous painting in the Louvre is the Mona Lisa. The artist who made the Mona Lisa is Leonardo da Vinci. Leonardo da Vinci is also the name of the main character in the cartoon Teenage Mutant Ninja Turtles. Leonardo da Vinci is from Italy. The thing that Leonardo da Vinci usually holds in his hand is a katana. The country of origin of the katana is Japan. The answer is Japan. So I just find this absolutely astounding that this model is one model, hasn't been fine-tuned, and it can bring together all these unrelated topics together. And this is exactly what scale gives you. This is why everyone's so excited by it. And it has huge implications for the conversational kind of AI space, I think, as well. Google took this a step further. So they've trained a model called Minerva. This solves mathematical problems in high school. Now, what's really cool about this is they got a new state-of-the-art result, but they went from 7% accuracy to 50% accuracy on this math data set. And that's something that ML forecasters didn't think was possible for another few years at least. So this stuff is moving incredibly quickly. These large language models can do stuff we didn't think would be possible. And the way this works is we fine-tuned Palm, Google's model, on text from like LaTeX code that's in archive papers or kind of blogs. And this is what you get. So this is an example. This is looking at a position vector of a particle. It's asked to find the speed, and it can go through all of the working, and it knows how to differentiate with respect to time, and you can get the speed of the particle there, which is 3/4. So one of the main things which it uses to get good accuracy here is something called chain of thought reasoning, or chain of thought prompting. So if we look at this example here, we have the number of tennis balls that Roger has, and it's asking how many do we have. In the first example, it just puts the answer straight out. The answer is 11. But you can see then when we go to the one we care about, which is the number of apples in a cafeteria, it gets it wrong. But when we introduce the chain of thought reasoning on the right, which is highlighted in blue there in the prompt, it actually then gets it right. So it's gone through kind of what it's thinking, that it starts with 5 balls, there's 2 cans of 3 tennis balls, and then it adds them together. So this is one of the main things which Google has used, along with kind of majority voting as well. So we've now got the building blocks to put together here. So we've got large language models. They're amazing at scale. They understand lots of things. They're kind of a world model. We've got few-shot learning. That's when we give it a couple of examples of how to solve the problem so it can learn the structure, learn what we want to do. Then we have chain of thought reasoning, which I just went through there, where in the prompts, we have that. It increases accuracy. And we have the NER model, which, if you cast your mind back, was the weighted average of different severity of errors in our ASR outputs. So this is the cool part. So this is GBT3 Playground. And we've set up the problem as follows. So we've got the reference and the recognized transcripts here. So you can see the first one, this has been confirmed by the Pentagon, and there's a one-word difference which it's been swapped to hasn't. So then we give it chain of thought reasoning, which is underlined in dark blue. The word has is reversed, which causes misinformation about the message. Therefore, the error is likely serious. We do this again with the executive example, where we've just swapped an and in. The error is minor there. And now we're going to give it the one we care about, which is when we omit suspected before murderer. And the last thing in the prompt is result : and it outputs then what we have at the bottom here, which is highlighted in green. So it outputs the word suspected has been omitted, which changes the meaning of the message. Therefore, the error is likely serious. So it gets it right. It's using its world knowledge to give us the severity of error, and we can use that now to calculate the NER metric. And why is this good? So let's look at the same examples. Top right, the 5-year-old kid one, which gave 125% word error rate. We now just say, there's one minor error there because the I'm and the I am. There's no problem there with the 5-year-old kid part. So that's just penalty of 0.25 for the minor error over 4. It's a 6.25% NER. Then in the other example, that's one serious error there because it causes misinformation about the message. 1 over 5, 20%. This tells a much better story that's aligned with human judgment. And it's all been automated with large language models. You don't need human in the loop. This is early days, though, with this research. We want to look at how it deals with multiple errors. How does it correlate with word error rate? Is it too subjective? Some of the questions we're kind of asking. That's all from the talk. I hope you enjoyed it. Come and say hi at the Speechmatics stand if you want to have a demo of our speech-to-text. Come and see it working in 48 different languages, see if you can break it. You can also scan this QR code. You get 4 hours free a month on our portal for you to try out and see how accurate we are. But yeah, thank you very much for listening.